And just to telegraph the punchline, we have learned all kinds of surprises. And so the subtitle here is It's a Whole New Jupiter. But why don't we start with what we're doing and why? So Juno is, first of all, the first solar powered mission to Jupiter, first solar powered mission to go as far as it's gone. That is as far from the sun. We have 8 science instruments and an outreach camera as well, which we're now using for outreach and science. And we've learned to use the stellar compass, the star camera that helps us navigate. We're using that to do science because, we'll use anything we can find. It's a spinner. It's orbiting Jupiter pole to pole, and we'll talk about that a little bit. And there's some other statistics here and stuff that you guys can read on your own. I won't read them all out loud. And I'll point out, though, I always like to mention this, that Juno is a principal investigator mission. What that means is there's one person in charge of the whole thing, a principal investigator. It was proposed as a proposal to NASA and then funded, and we put together the team, and Scott Bolton, who's the PI, is in charge of everything, and then he delegates the authority to a bunch of other people. Normally, NASA does only really, does all their really large missions with a team managed by a whole group, essentially managed by committee. And the small stuff is done by PIs. Juno, at the time it was selected, was the largest principal investigator mission NASA has ever selected. And I think they got enormous bang for the buck. We really showed that it works better that way. If you put together a good team that works well together and you have a PI who knows what he's doing and is willing to, delegate what he needs to delegate and make decisions when he needs to make decisions, it just works way better than running by committee. So I just wanted to put that little plug in there. Scott's the PI, I'm the project scientist. So he delegates most of the authority to run things day to day to JPL, to a project manager and a project scientist. And we talk with each other all the time, and the scientists get to make the decisions instead of the engineers, which has its pluses and minuses, but I think worked really well. All right, on to science and what we care about and why. So the first question you ought to ask when I say we sent a spacecraft to Jupiter is, why did you do that? What are we trying to learn? And basically, the key thing here is that if you look at our solar system and you look at what it's made out of, 99% of the mass is in the sun. But of the leftovers from the sun, more than 2/3 of the mass is Jupiter. Furthermore, Jupiter formed first before the other planets and much of the material in the solar system. So in a very real sense, planets like the Earth formed out of the leftovers from Jupiter. So if we want to understand how did the solar system form, it's important to understand how Jupiter formed. If we want to understand any of the major stuff about the solar system, Jupiter might very well play a role because it's so big and because it's such a big part of the solar system all by itself. So we had 4 main goals for Juno. Understand the origin of Jupiter and by extension, the origin of the solar system. And the key pieces of information for that, as I'll talk about in a little while, were understanding how much water is in Jupiter and understanding what its dense core in the middle of Jupiter is like. How big is it? How much material is there? Is there really a dense core? We didn't know that till we got there. On top of that, we want to understand the interior of Jupiter, understand how it works inside the planet, because all we see from the Earth is the tops of the clouds. I'm sure probably all of you have looked at Jupiter in a small telescope. And with a decent telescope on a clear night, you can see the stripes, the belts and zones, and you can see the moons going around, and you can see the great red spot. But all of that is in the top tiny fraction of a percent of the planet. Most of what you're seeing is right there at the surface, and most of the planet you don't get to see remotely. So we're trying to peer beneath the clouds and understand Jupiter. That involves trying to understand the atmosphere. While we're there, measure the magnetosphere, all the Jupiter's magnetic field and all the charged particles trapped in the magnetic field. So I don't want to go on too long about each of these science goals, but I'm happy to talk about them if there's questions near the end. I want to point out a couple of things, though. One is the orbit was key. Our prime mission for Juno, the plan was come in over the pole, close to the planet, very close, within a 20th of the radius, and out the other side. That only takes a couple hours. Then we spend days, weeks actually, 53 days was the orbit, out far from Jupiter, and do it again. And the advantage of that is, first of all, we don't spend a lot of time in the high radiation zone that's going to fry all the electronics, because this stuff shown nearby the planet, that's high energy electrons and protons trapped in the magnetic field that could destroy the spacecraft. And then second, by ducking in under it, not only do we avoid that, but we get to look at the planet extremely close. And because it's a polar orbit, as Jupiter rotates every 10 hours, we can choose whatever longitude we want just by adjusting the timing each pass, so we can make a good map of the planet. So the plan was 32 polar orbits, use gravity to understand the interior, because gravity comes from the whole planet, a magnetometer to measure the magnetic field, because that comes from the liquid metallic hydrogen deep inside. I'm going to pause there for just a second, because I can't help it every single time I say that phrase. Liquid metallic hydrogen. So hydrogen gas, the lightest element there is, here on the Earth, release some hydrogen and it floats up into the sky. On Jupiter, it's so big, at 300 times the mass of the Earth, the gravity is so intense, the pressure is so high, that if you go down a quarter to a third of the way into the planet, hydrogen is squeezed so much from the pressure that not only is it a liquid instead of a gas, but it's squeezed so much you effectively have squeezed the electrons right off the atoms. It conducts electricity. It's a liquid metal. So it's the swirling motion of that liquid metallic hydrogen that makes Jupiter's magnetic field. By measuring the magnetic field, then we're measuring what's deep inside the planet, because we're measuring, in effect, that ocean of liquid metallic hydrogen. And then a key instrument we brought that hadn't been done before, never to a giant planet and almost never to any planet, was a microwave radiometer. The key point there is the radio waves that the radiometer can see come from beneath the clouds. We can see through the clouds. Now, microwave radiometers, or radiometers in general, they're measuring because it's measuring the radio waves, and the radio waves are given off by any object that's not at absolute zero. What we're doing is measuring how hot it is, basically. It's a little more complicated than that, but the basic scenario is if you take a lump of stuff, any stuff, and you heat it up to, say, room temperature, it glows. Now, if you heat it up hot enough, it would glow in visible light, white. But if you let it cool off from that, it'll glow red. If you let it cool off even more, it'll glow in the infrared. If it's cooler than that, it's going to glow in the radio. Now, it's actually giving off all of these different wavelengths all the time, but what I'm describing is where the peak is. So if I look at it with radio waves, the hotter it is, the brighter the radio signal. I don't need to send a radar in. I don't need to transmit anything. I can just passively watch. And Jupiter has the nice advantage for doing that it's hotter on the inside than the outside. And that's because it's so massive that it's still cooling off from its heat of formation 4.5 billion years ago. So the result of that is the deep interior of Jupiter is hot, the top of the clouds is cold, and by looking with a microwave radiometer, we can see through those clouds. So that's in some ways our key instrument. Then there's a bunch of other instruments we put on it to measure the fields and particles that we pass through, to look at the aurora, a visible light camera to take pretty pictures, and we'll talk about some of those as we go along. All right, that's way too much time to spend on one slide, so let's move along. So the obvious question is, what have we learned? And the first answer is humility. Before the spacecraft got to Jupiter, everybody had ideas about what we were going to see, and we had expectations of what Jupiter would be like and what we were going to measure and what we were going to figure out. We had a bunch of different ways in which we were doing things for the first time, measuring Jupiter in ways that hadn't been done before. And in every single one of them, we were surprised. Every time we measured something that hadn't been done before, it didn't look like what we thought we were going to get. So I'm going to tell you about some of those surprises, but the summary, this is a quote from Mike Jansen. He's retired now, but he was one of the key scientists on Juno. When we first started getting data from Jupiter, we got pictures over the North Pole of Jupiter, and they didn't even look like the same planet. You look at that picture and your first reaction would be, wait a minute, that's not Jupiter. We got measurements with the magnetic field, and it was way more complex and didn't look like what we predicted. The first data with the microwave radiometer was much more complicated than we expected. And people were sort of buzzing about all of this in the first couple of days, saying, what's going on here and what does it all mean? And Mike basically just said, face it, guys, it's a whole new Jupiter. And that's been the theme for the last 5 years. It's a whole new Jupiter. What we've learned from Juno really revolutionizes our understanding of what Jupiter is and what it's like and how it formed. Okay, so I can't possibly give you all the surprises, but here's half a dozen of the big ones. And I'll try to save lots of time at the end for questions so we can talk about other things if you want. So to me, in no particular order, these are some of the key surprises. So the deep atmosphere is not well mixed. What does that mean? Well, if you look at Jupiter, it's a giant ball of gas. The sun doesn't penetrate very deep. Sunlight doesn't go very deep into the planet. The clouds that we see are water and ammonia clouds. Those are way up high in the atmosphere where it's cold enough to get liquid water. So if you go down into the planet, tiny fraction of the radius to where the pressure is only, say, 100 times the pressure here on the Earth, you should be below all of that stuff. And everybody, before we got there, thought it would be well mixed. In fact, back in the 90s, when we dropped the Galileo probe into Jupiter, the expectation was you'd only have to go to about 20 bars, 20 times the Earth pressure, before you got to where it was well mixed. So they designed the probe to do that. It got down to 22 bars and still wasn't seeing things steady out. Everything was still changing, especially the water. And so the conclusion was, well, we didn't go quite deep enough. We proposed to a mission that, to an opportunity where NASA said, you can propose to do a Jupiter polar orbiter with probes, multiple probes, send them in a bunch of places, then we'll really find out what it looks like, 3 or 4 probes. And we said, that's not the way to do it with the microwave radiometer. Instead, we'll get to see the whole planet. And it's a really good thing we did, because what we saw is as deep as we can see, several hundred bars, hundreds of kilometers down into the planet, it doesn't look well mixed. It's still got structure, and we'll talk about that. We saw clusters of cyclones around the North Poles. We see a dense core like we expected, but it's dilute and fuzzy. It doesn't look anything like what was thought it to be. The belts and zones that we see go 3,000 kilometers deep into the planet. The magnetic field is way more complicated, and I'll show you some of that, and is being sheared by the deep jets. It's changing. We see shallow lightning way up at the top. That was a big surprise, which doesn't sound so impressive until you realize that you're seeing lightning at a height in the atmosphere that is way too high ordinarily to have liquid water. Here on the Earth, to get lightning, you need liquid water. And our conclusion, tentatively at least, is what we're seeing is lightning because of essentially Windex, ammonia and liquid water, ammonia acting as an antifreeze to let the water get high enough in the atmosphere to make lightning. All right, so let's talk about some of those things in more detail. We'll start with the deep atmosphere is not well mixed. So on the left, actually, let me see, I guess I don't have a good picture of it. On the left, if you look, this is latitude across the bottom. So the south to the left, the north to the right, and pressure vertically, so think of that as depth. What we see when we measure it with the microwave radiometer is opacity, how much the atmosphere absorbs our microwaves, and temperature. And if you put those together, that helps you figure out how much ammonia is there. And what we saw is near the equator, but not quite at the equator, the ammonia is reasonably uniform from deep down up to the surface. But north and south of it, it's not. You're missing ammonia over here. It's more or less the same across latitudes over here, but with depth, it's changing. You have ammonia disappearing and then coming back again. So there's all this structure going on way deep in the atmosphere, much deeper than anybody expected. The water cloud is way up here. So this was a big surprise. And the conclusion, oh, and on the right here, I'm showing, hang on, I got all, it's good to see all your faces, but it's not helpful because it's covering my screen. There we go. Okay, so on the right here is the ammonia without the picture on top, so it's a little easier to see. And on the bottom right, we're showing lightning flashes. And the reason for putting all of that story together is we think what might be happening is somewhat like a hailstorm on the Earth, only on a hugely grander scale. What we're calling mush balls form. So think of a water droplet with ammonia gas partially dissolved in the water that acts like antifreeze, so it gets to be quite a bit colder before it finally freezes. With the outer surface frozen water, so you have ice on the outside, liquid water on the inside, and an updraft in the air. So what that does is it starts down where it's warm enough, blows it up high so it's really cold. As it picks up more material, it gets bigger. That makes it fall, and it starts to come down again. And you can do multiple cycles of that. That's sort of what happens with a hailstorm on the Earth, of course, without the antifreeze. But here, what that might mean is that the ammonia is getting hidden in these mush balls, and that would sort of explain why we have this vertical structure, because you get ammonia down here where they melt, and you're missing ammonia here where they're carrying it up to the top, and then at the very top, they don't reach that high. And the storms carry the stuff up and down, could explain the lightning, why we can see lightning way up at the very top, because these updrafts would be carrying the mush balls. So there's I hesitate to even call it a theory. There's an idea that we're exploring that maybe could explain this. A lot of work to be done, and obviously something complicated, showing Jupiter's way more complex than we expected. It's not just a simple ball of gas down underneath. Why can't I get it to change slides? Let's try that. Okay, so the shallow lightning, we know because we used the star camera that's supposed to be used for navigating to look at the planet in the dark. And we found flashes, lightning flashes, and from the size of them, we can tell that they're much higher in the atmosphere than anyone's ever seen lightning on Jupiter before. And that indicates maybe that they're formed from ammonia water rather than just water. Lightning is usually on the Earth is frozen water, so ice, and liquid water and water vapor, and you combine them, and the ice picks up electrical charge and then discharges it, and it causes lightning. But to do this on Jupiter at this height, you have to have ammonia mixed in. So that was an interesting surprise. Then we see an example of looking with the microwave radiometer again, how deep the storms go on Jupiter, and they go much deeper than you would expect. Remember, about 8 bars is where water freezes out, or condenses out in Jupiter. That's where the water clouds are. You go deeper than that, it's too warm to have liquid water. You go higher than that, and the water starts to freeze. So what you would expect, what everybody expected before we got there, is all the weather would be up at the higher levels where sunlight is stirring things up, where clouds can form, where you can make storms and things like that. But we saw with the ammonia, there was something going on, big structures down deep. And what we can see here is smaller structures. And by smaller, I mean the size of the Earth and smaller, because the Great Red Spot is a little bit bigger than the Earth. Those smaller structures also can go deep as the microwave radiometer can see. So here's when we flew over the Great Red Spot, the visible light picture, that's a Juno cam picture. So that's the same wavelengths your eyes see, and you see the Great Red Spot. And then underneath it, the color coding here is showing how bright the microwave signal was. And what you can see is we definitely see the Great Red Spot here as a hot, brighter signal here, a little bit to one side, and cooler in the center. And that's sort of what people expected. But as you go deeper, it fades away around where the water cloud is, and then it picks up again. And we still have a strong signal as deep as we can see, only now the Great Red Spot is hot at the bottom. So we don't know from this data the roots of the storm. We have gravity data that tells us it's somewhere maybe as deep as about twice that depth, but not much deeper. But nonetheless, that's much deeper than people thought the Great Red Spot would go. And we have to explain now how storms are forming that go so deep into the atmosphere with basically nothing to stir them up, right? There's no mountains or ground or sunlight or anything like that to generate the storm. And then these are a couple other examples of smaller storms where you see similar things. Here's one that fades away where we can see it, and here's one that continues as deep as we're able to see. Picking up another one of the surprises, this is the infrared picture because it shows it better. But that's the North Pole of Jupiter on the left and the South Pole of Jupiter on the right. And what you're seeing is circumpolar cyclones. They look like crystalline structures. That set of 8 cyclones in the north surrounding a central cyclone has been there for the whole 5 years, basically unchanged in its pattern. Those things are comparable. The big ones may be the size of the United States, and the little ones around it, think Texas sized or so. And in the south, there's similar structure, only instead of 8, there's 5 in a central cyclone. And this one, we've actually seen a 6th cyclone kind of force its way in and then get pushed out again. So it's pretty stable at 5, but maybe not quite as stable as the set of 8 in the north. If you look at the dynamics of a planet, a giant ball of gas like Jupiter that's spinning rapidly, 300 times the mass of the Earth and spinning every 10 hours, more than twice as fast, you expect that cyclones, storms, would drift north and south. If you just work out how the air flows, how the atmosphere flows, it makes sense because the thing's a sphere, right? So if you pick something that's partway up in the northern hemisphere, then the bottom part of it, in order to keep up, has to spin a little bit faster than the top part of it to match up with the rotation of the planet, because it's rotating on a larger radius. We work out the math and see what that does, and that's going to result in the thing drifting north or south, depending which direction it's spinning. So it sort of makes sense that the cyclones would all drift up to the North Pole, but what we don't have a good answer for is, why don't they merge into one big cyclone? Why do they last long enough to go up to the North Pole and hang out there for 5 years without any obvious change? They could have been there for 50 or 100 years for all we know. Why are they the sizes they are? Why are there 5 in the south and 8 in the north? One more asymmetry in Jupiter. Remember, when we looked at the microwave data, we saw that not only was there this structure, but that big band at the equator wasn't quite at the equator. It was a little north, and the deficit in ammonia was further north than that. So Jupiter was already asymmetric in that picture. We're seeing more asymmetry here, north and south looking different. If we look at the gravity measurements, remember I said there was a fuzzy core. So everybody expected that down in the center of Jupiter, there'd be a dense core of the heavy elements. They should sink to the bottom, right? The light stuff, the hydrogen, the helium, and the gases should be up at the top. And most of the heavy stuff, most of the dense material, should sink down to the middle. So we expected, depending on how Jupiter formed, somewhere between 3 and 20 times the mass of the Earth to be in a dense core in the middle. Well, we found a core, and it's in the ballpark of that mass, but it's diluted, it's fuzzy. Somehow it stretches out to half the radius of Jupiter. So that leaves us with all kinds of questions about how Jupiter formed that don't match up really well with our ideas from beforehand. One of the ideas that people have come up with is, well, maybe what happened is early in Jupiter's history, it just got hit with something really big, smacked into it, stirred everything up, and it hasn't settled down yet. So it's possible that that will work out, but it feels kind of specially tuned. It's not a very simple explanation because the timing has to be right and the size has to be right and so forth. And you have to form something comparable in size early with Jupiter. Maybe it has to do with how Jupiter formed. If the dense stuff came in later instead of earlier, then that could have made it not fall all the way to the bottom without melting and spreading out and so forth. If you think of a sort of simplest model for how the planet could have formed in the early history of the solar system, if you start far enough away from the sun where it's cold, then water is a solid, it's ice. So chunks of ice, when they bang into each other, can stick. You get enough of it, it starts to have enough gravity so that it pulls things in. Well, what's it going to pull in first? It's going to pull in all the dense stuff first, so the ice, and carrying with it heavier elements. And eventually, when there's enough mass, then it starts sweeping up the gas. It's got enough gravity to hold the gas, and the envelope forms on top. But if you do that, you get this nice sort of gradient of how the planet formed, and all the really dense stuff should be in a tiny core down in the middle. Tiny meaning only 20 times the mass of the Earth, right? Remember, Jupiter's 300 times the mass. But that's not what we see. So either it formed in some more complicated way, or something stirs it up so that the dense stuff can't really sink all the way to the middle, or the composition is somehow different. So we have lots of problems to solve and no good answers yet, really, which is fun if you're an experimentalist. Okay, so let's see. Here's a few things all at once. I want to start, though, with this. You see the magnetic field in the upper left? This is Jupiter's magnetic field. So at first, it looks like a dipole, but what's that? There's what we're calling the great blue spot right at the equator. The magnetic field goes down. If you look at the southern hemisphere, it looks kind of like the Earth's dipolar field, kind of pretty simple and normal. And you look in the north, and it's this big complicated mess. Let it tilt down. It's not playing that well over Zoom, I think. But you can still see how tangled the magnetic field is in the north. So Jupiter is very asymmetric and has much more structure in the magnetic field, which means at least part of the magnetic field is generated much closer to the surface. Because if it were all down in the middle, I'm going to pause this. If the magnetic field were generated way down in the center, then any complexity would fade away. It drops with distance. It actually drops as the cube of the distance for the dipole, and then even faster for everything else. So all the complexity is invisible from far away. The only way we can see a field this complex with our spacecraft skimming above the clouds is if that magnetic field is generated instead of down at a third of the way down towards the center of the planet, maybe half that or less, 10% of the way down to the center of the planet. So it's not the liquid metallic hydrogen that's generating that part of the field. And what we think is going on is if you squeeze molecular hydrogen enough, it conducts electricity a little bit, like sort of salt water. And the swirling motions of that molecular hydrogen are enough to add to the magnetic field and add all this complexity, even though the bulk of it is still generated by the liquid metallic hydrogen. On top of that, if you look at the magnetic field and put a map over that great blue spot, let the movie run a little bit again, and I'll stop it when we get to the great blue spot so you can see it both ways. There we go. So you see how there's this place where all the field lines are coming here, like it's got its own little South Pole right there, right, near the equator. If I put that on a map over here on the right and superimpose on it the profile of the winds of Jupiter, the belts and zones that we see, what you can see is the magnetic field looks like it's being sheared by the winds. When the wind is going to the right, the magnetic field has been pushed to the right a little. Where it's going to the left, it's been pushed to the left a little bit. And that ties in nicely with our gravity measurements, shown here in the lower left, where as the spacecraft falls past the planet, the gravity of Jupiter makes it speed up and slow down. And these belts and zones, because they're moving, I'm going to pause for a second in the lower left, these belts and zones are moving in opposite directions. They're jet streams moving to the right and to the left. And because of that, that means they have slightly different density and they bulge out different amounts. So as the spacecraft falls past it, it's going to speed up and slow down as it goes past these belts and zones. We can actually measure that and determine how much mass is in those belts and zones, and therefore how deep they are based on the signature from the gravity. And the conclusion from that is they go about 3,000 kilometers deep into the planet, which is a really interesting depth, because that's about the depth where the molecular hydrogen conducts electricity enough that it should affect the magnetic field. So we think what might be happening is some of the complexity in the magnetic field is driven by the belts and zones. And likewise, the depth of the belts and zones may be driven by the magnetic field. When they get deep enough to where they conduct electricity a little bit, the magnetic field slows them down, and that's why they don't go any deeper. On top of that, Kimmy Moore looked at the old data from Voyager, from Jupiter's magnetic field, which, even though it was nowhere near as precise as our data, was 30 years earlier, and compared it with the Juno data, and was able to show that the magnetic field has actually been changing in those 30 years, and it's changing consistent with being dragged along by the winds. So we now think that the magnetic field, while complex and asymmetric, is also windblown. Jupiter's huge jet streams are actually distorting the magnetic field. Okay, so I gave you a little taste of some of the surprises. I want to spend time answering questions so we can talk about whatever strikes your fancy as something to pursue. But I also want to give you a little bit about what the extended mission is going to look like, because we finished our prime mission, 32 orbits, this past August, and the spacecraft is still working. NASA says we can keep running, and one of the key things we're going to do is explore Jupiter's northern frontier. So those orbits, when we started out, were coming in with the more or less parallel to the equator, so that the perigeo, the closest point to Jupiter, was way down here. And that was great for studying all the parts down near the equator, but we were getting a little far from the planet by the time you go over the poles. Well, towards the end of the prime mission, Perigeo 34, we have this light blue orbit. Perigeo has moved north, and that's because Jupiter's not a perfect sphere. Because it rotates so fast, it bulges at the equator, and that shifts the orbit and makes it rotate downward, which means the closest point, the perigeo, is moving upward. So now, in our most recent orbits, we get to see the region over here up at around 30 degrees north with the greatest detail. But if we wait long enough and survive, by the time we get to perigove 75, so twice as many orbits, the perigove will be way up at 63 degrees north and will be much closer to the pole. So all the good data that we got near the equator, we should be able to get something similar up near the poles. So that's Jupiter's extended mission. Let's see if I can get the slide to change. There we go. There's a bigger picture, which is nice because it also shows that as we come in over the pole, so remember, we started out with these orbits out here, perigove 1, from way out here, over the pole, really close to the equator to get good data, and out the other side, and duck in inside the rings and the moons and all that stuff, and the radiation belts, so we would be safe. The orbit is gradually shifting. Perigove 34, we flew by Ganymede, so we got a single close flyby of Ganymede, looked at it with a microwave radiometer for the first time ever, and stay tuned for results from that. It's not ready to be too public yet. But as we continue, by perigove 45, we're going to fly by Europa, which ought to be really interesting. Maybe we could learn something about the thickness of the ice. And Io with the volcanoes, and we can learn something about the interior of Io, both from the infrared and microwave, and especially from the gravity. And if we make it that far, we might even fly through the main rings of Jupiter, which are nothing like Saturn's rings, but may still be dense enough to either see something really interesting or have a piece that's a little too big, hit the spacecraft and just kill it for its final orbit. Okay, so I obviously rushed through that pretty fast and gave you only a thumbnail sketch of some of the surprises. But as is, it's 8:40. And I want to save time for questions because that's the fun part. I have lots of other slides I can use for backup if you ask me a question relevant to them. I'm going to stop sharing the screen for a moment so I can see your faces. And I might bring it back up if it's needed to answer questions. So I hope that I gave you enough teasers that lots of people have lots of questions, but let's see where we are.
I've got a question.
Yeah.
I find it very fascinating that the North Pole of Jupiter has 8 cyclones and the South Pole has 5.
Right.
And I was thinking, if I'm not mistaken, that Saturn has an octagonal shaped North Pole, I think. And
right.
I was, in doing comparisons of the planets, comparative planetology, I guess, I'm wondering if there might be some kind of a relationship between the two planets. Saturn, I think, would probably come closest to Jupiter within our solar system when it comes to planets. Is there anything that you can say about that?
Yeah, but it's in progress. So yes, you're absolutely right. That's one of the key things to look at here is, okay, why is it different in the north and south? Why does it look different from Saturn? What are the ways in which it looks similar? And we know some of the key things that matter. So how fast the planet rotates matters. The sheer size of it matters because that changes the heat flow out of it, and it changes the speeds at which things are happening. Then if you just postulate, okay, I've got a cyclone on Saturn and I let it drift north, depending on the size of that cyclone and the way it forms, they can merge and they can make something like that hexagonal pattern that we see on Saturn. If you've got jet streams up by the pole that are cyclonic in nature, but are like one big cyclone rather than the little ones. And if you look at Jupiter and you say, okay, I have cyclones and I have anticyclonic motion on the outside of it, sort of a shield, then, and we see that when we look at it, we can actually see that, yeah, there is something sort of counter-rotating. It's not quite that simple. Then they won't merge and they'll sort of bang into each other. And if you pick their sizes right, you can make it work out and predict that, yeah, it should look like it, what we see at Jupiter. but that doesn't tell us why are the sizes of the cyclones that. Why is that the preferred size for cyclones in Jupiter's northern hemisphere? Why do the ones in the south look a little bit different? It's fairly well understood why they drift north and south. The energy ultimately for those things has to come from Jupiter's rotation combined with the heat escaping from the planet. But exactly how you get that, we don't know. So people are trying to model it. We're using models based on what happens in the Earth's oceans, because, or at least that's part of it, because Jupiter's atmosphere, unlike the Earth's atmosphere, goes much, much deeper. There's no real, the Earth's atmosphere is very nearly two-dimensional. It's got a surface underneath that affects things a lot, and a surface at the top. The atmosphere itself is fairly thin. On Jupiter, we don't have that. What corresponds to a surface maybe is 3,000 kilometers in, where the magnetic field is affecting things. But it's clearly not as simple, right? And those cyclones don't rotate around with the planet at the same rate as the magnetic field on the inside. So they're not directly connected to it. So all of that is really a long way of saying, yes, you're asking the right questions, and no, we don't really have the answers yet. But remember, the extended mission is going to get us a lot closer to those cyclones. So one of the key things we hope to do is see how deep they are. And that may tell us a lot.
Yeah.
So Steve,
Thank you.
is the core contributing very much or at all or significantly to the magnetic field? Or am I understanding you to say that the magnetic field is generated by these more superficial or things closer to the surface, that are affected by the winds, by the storms, things like that, and these are related to these layers of gases that have become metallic, right, and conductive? Is that a fair statement?
So I want you've divided it into two, and I want to divide it into three.
Okay.
So think of three layers. There's more, but think of three basic layers. Way down in the center, there's the core, and that's the denser materials. And what I mean by denser is more or less, really, I mean anything denser than helium and oxygen, but think of it as the rock part of it. What would have been, a rocky planet like the Earth if it weren't surrounded by, much greater fraction of hydrogen and helium.
But it's not metallic. It's not metallic, though.
Right. Well, there might be iron in there, but
Okay.
its metallicity isn't, the fact that it conducts electricity isn't a big factor in the magnetic field, because it's way down in the center and it's relatively small. It's only a few times the mass of the Earth. Okay. Now,
Okay.
that core, there may actually be a core that dense, compact core like that way down in the middle. But what we found with gravity is something that's comparable in mass to that, but spread out over sort of half the radius of the planet. Okay. But that's still not where the magnetic field comes from. Then on top of that, the next layer up, and again, there's other layers, but we'll think of this as sort of three parts. The next layer up, think of liquid metallic hydrogen. So that's pressure 2 million times the pressure here on the Earth instead of 10 million. Okay. So still ridiculously high pressures, high enough that hydrogen gas, which is the bulk of Jupiter, conducts electricity and is a liquid metal. That's where most of the magnetic field comes from. You get a magnetic field if you take something that conducts electricity and you swirl it around, basically stir it up. It can, in a rotating body like a planet, it can form a dynamo where it sort of reinforces itself and generates a magnetic field.
And that's how you can end up with a blue spot that has a magnetic field, right?
Not yet. That's how you get the bulk of the magnetic field.
Okay.
And then the fine structure that we saw that was the big surprise, like the blue spot, probably doesn't come from the liquid metallic hydrogen, because the liquid metallic hydrogen shouldn't form till the pressure gets up to a couple megabars, a couple million times the Earth's pressure. And that's got to be at least 15, 20, maybe 25% of the way into the planet. Now, when you measure magnetic fields, one of the first things you learn is if I have a source over here to generate a magnetic field and I measure it over here, the further away I am, the more the magnetic field fades away. And it doesn't fade away just as 1 over the distance squared, the way, light does or something, because it's a field, it's not a scalar, right? It's got direction to it. And it turns out if you have a dipole field like the Earth's field, so basically like a bar magnet, that fades away as the cube of the distance. Anything more complicated fades away faster. So because we're measuring it from up above the surface, we know how far away we are more or less from the liquid metallic hydrogen. And we didn't expect to see that complexity that we see, because even if it was generated down there at the liquid metallic hydrogen, it should have faded away by the time it got to where we are to measure it. Only the less complex stuff should have made it up that high. We weren't expecting a pure dipole, but we weren't expecting anywhere near the complexity we see. So that's part of what's leading us to believe that the magnetic field is being affected by molecular hydrogen up much higher in Jupiter's atmosphere. That's probably at a few thousand kilometers in, where the belts and zones are stopping. So the great blue spot is in a magnetic field that's generated from down in the liquid metallic hydrogen, but it seems likely that the fact that there's a great blue spot there is really dictated by motions in the molecular hydrogen that's still a gas at a few thousand kilometers into Jupiter. So that's the 3 layers I'm talking about. The upper atmosphere that's only a few thousand kilometers deep that starts to conduct electricity a little bit at the bottom. Then the liquid metallic hydrogen that's deeper and generates most of the field. And then the dense core in the middle, which unlike the Earth's core, isn't the source of the magnetic field. It's just where all the dense heavy stuff fell down to the center. Obviously, this is a much more complicated picture of Jupiter than I would have given you, 6 years ago before Juno got there. But that's what makes it fun.
Yeah, it is a new Jupiter. Thank you.
Sure.
I wanted to know about the UV spectrograph and why UV? What are you discovering?
Yeah, let me see if I've got, I'm going to bring that PowerPoint back up and see if I have some nice pictures from the UVS. So it was there primarily, here we go. It was there primarily for looking at the aurora. So here's a good one. Okay, so you see that? Okay, what we're looking at here is ultraviolet images of Jupiter's, in this case, it's the North Pole, I think. Well, on the right is certainly the North Pole. That might be the south on the left. And what you see is the Northern Lights, the aurora. And if you look at this part, this is a trail on the planet left by one of Jupiter's moons. I think that's Io. It's a blow up, right, of this little line here. So what's happening is charged particles in Jupiter's magnetic field are streaming down the magnetic field lines, smacking into the atmosphere, the upper atmosphere, and making it glow. And the ultraviolet spectrometer is catching pictures of that. And we learned a few interesting things. One of the key things we learned is something that you can't see from the Earth. From the Earth, you don't get to look at the North and South Pole directly. You're looking at them at a very shallow angle, and you're only seeing the daylit side because Jupiter's further from the sun than we are by a lot. So we're always on the sunny side of Jupiter. And what we didn't know until Juno got there and looked at it in the ultraviolet is that this part, the polar part of the aurora, lights up in the daytime and goes dark at night. So it's not lit by sunlight that's doing that. These are high energy particles hitting the atmosphere, but somehow we're not hitting as much in the nighttime as they are in the daytime. And we, of course, would never have known that if we weren't there to look at it with the ultraviolet spectrometer over the poles. Lots of other stuff. We're measuring the electrons that come down the field lines and hit the atmosphere, and the electrons that come back up. We see the auroral tail from Io. So that's, think of particles from Io's volcanoes interacting with the magnetic field, streaming all the way down and hitting the planet. And then even though Io is at one spot, because the waves, the electromagnetic waves or plasma waves that affect those particles can bounce back and forth, because the moon Io is disturbing the magnetic field around it and disturbing, therefore, the particles that are around it. You can get a trail that moves or that marks up the planet in this big curving arch. That's it. You look at it and it looks like, oh, this is left behind as Io orbits, but that's not what's happening. It's actually being generated in real time with Io, the magnetic footprint of Io. If you follow this field line, it goes to Io. You follow this field line, it doesn't, but particles can move from one magnetic field line to the other preferentially in a way that leaves these marks. Anyhow, when you look at that and see, zoom in on it, you see all this structure in it, and it actually splits into two. So that's another surprise that we've been investigating. Then the ultraviolet spectrometer measures not just pictures, but different energies of ultraviolet light. And that's the picture over here showing what we can learn by essentially the colors of the UV that we look at. All right, so that's sort of a, obviously, only a thumbnail sketch of what we can see with UVS. But perhaps a better way to think of it is, because of our orbit, we're out there on magnetic field lines that flow down to the northern and southern poles of the planet, right? Everywhere on the planet, actually. We cross all the field lines. We measure the particles that hit the spacecraft that would otherwise be streaming down and hitting the planet. And then a short time later, with the infrared and ultraviolet cameras, we take pictures and measure the aurora generated by those particles. So it's a really good orbit for studying what happens and what causes the aurora on Jupiter. And what we found is the mechanisms that accelerate the particles at Jupiter are different from the mechanisms that accelerate them at the Earth. We see some of the same things, but the really most energetic stuff is not being accelerated the same way it is at Earth. So more mysteries and surprises, and there are actually people who can give you better explanation than that. I'm not an expert on the magnetospheric physics, so I'm glossing over things because I don't know.
I have another question for you.
Mhm.
I was just curious, do you know if any of the Galilean moons, the large ones, do they intersect at all any of the field lines, the magnetic field lines of Jupiter? And if so, if there's any visible effect
Yes.
on those moons?
So we see them in the aurora. Io is the closest of the Galilean moons, so obviously we see it the best. But Europa, Ganymede, and Callisto all also have signatures on the planet. We've flown by Ganymede and measured what's going on in the magnetosphere around Ganymede, and there's some debate about how Ganymede is affecting Jupiter's magnetic field and how Jupiter's magnetic field is affecting it. But yeah, there is some interaction going on, and there are particles that can stream from inward all the way out to Ganymede. It's because Jupiter's magnetic field is so much stronger and basically guides where all the particles go. It's much easier to see the impact on the aurora from Ganymede than it is to see the impact on Ganymede from Jupiter's magnetic field, but they are affecting each other. Callisto, I don't think we have the same kind of data set. We didn't get a good close flyby of it, and it's much further out. And I'm looking forward to what we learn at Europa and Io as we get closer.
Thank you.
Is
When
there any?
your
Uh,
perijos go north, is the spacecraft going to be able to actually fly through the aurora, or are you still too high up for that?
So tell me what you really mean by through the aurora, and I can try to answer.
Well, through where you see ultraviolet emission, is that too low?
That's too low. But what we think we will do is fly through and below occasionally the acceleration regions. So the particles that are making those aurora are accelerated in the magnetic field, either downward or upward. So some of it can be particles coming up from the aurora that get accelerated out, and some particles are accelerated down and actually hit the atmosphere and make it glow. And that acceleration region, we think, is we think we've come below it once or twice in our previous orbits, and expect that as we get closer and Perijove gets further north, we should, I hope, reliably get down below the acceleration region, and that'll give us a lot more information about what's going on. So you could kind of call that through the aurora, right? It's not.
Yeah, okay.
Steve, you showed I think in your first slide, that zone where all those highly charged particles are trapped. Do those interact at all with the planet, with the via the electric field, magnetic field rather, or are they
Yeah.
just stuck
So,
there?
in general, what happens, let me see if I can bring up a picture for that.
And I take it that that would be like a donut, right, all the way around the planet?
Yes,
Okay.
that's right. Every time I bring this up, I get a different thing shows up on my screen. I don't know what okay. Let's see if I have a good picture for that. I'm going to just kind of scan through all these things. See if I have one that shows the synchrotron belts. I don't have it in this particular slide deck. So I guess we'll settle for this picture.
Yeah.
So where it says trapped charged particles,
Mhm.
what those are electrons and protons for the most part, trapped in the magnetic field. And what that means is, if you think of an electron in the magnetic field, it's going to spiral. So if you try to make an electron go perpendicular to field line, it goes around in a circle instead. The magnetic field makes it go around in a circle. If you try and make it go parallel to the magnetic field line, it can just drift in that direction. The magnetic field doesn't affect it much. So a particle gets trapped on the magnetic field in the sense that it spirals around a field line and follows the field line north or south. But the field lines converge at the planet. The field's getting stronger, which means they're not quite parallel. And if you work out the physics, what happens is those electrons, if they don't have sufficient pitch angle, if they're not parallel enough to the magnetic field, they get up near the top and mirror and come back. So they're trapped in this like it's a huge tube that ends at the north and the south. But if they are by happenstance, basically aiming close enough to the direction of the field line, then they can penetrate down to where they hit the atmosphere and they get absorbed and disappear. So the result is, with charged particles gradually drifting in from the outside, occasionally hitting each other and things like that to change their positions, they gradually disappear close to the planet, and the bulk of them are kind of trapped near the equator, where the magnetic field is the lowest and the field lines are the most parallel. We see those high energy electrons in the radio. It's one of the reasons we had to go to Jupiter to do the radio measurements. It wasn't just to get close to the planet, it was also so that the radio glow of these electrons, the synchrotron emission, would be behind us instead of in front of us.
Yeah.
Then superimpose on that the ions, some of which come from gases from volcanoes at Io that kick gas out into space, and then ultraviolet light ionizes it to separate it into charged ions and electrons. That's now swept up by the magnetic field, which is rotating, every 10 hours with Jupiter, and has all this structure to it that I mentioned. And you wind up, we've discovered, one of Juno's discoveries is a high energy belt of ions quite close to the planet that's circling it, we think, like a donut, as you mentioned, but think of now more like a ring of high energy ions. And then we're getting a good look at all the electrons and their synchrotron radiation with the microwave radiometer, but we're still analyzing that data to build up a better picture of what these radiation belts look like. So they're not big enough to have a big impact on the planet itself. Jupiter is so massive, but they affect the aurora. They affect some things that we see. They definitely affect the spacecraft. That's probably what's going to kill Juno in the end, is the accumulated radiation. And of course, they're really interesting in their own right, trying to understand how these radiation belts work. Makes Jupiter a pretty dynamic kind of place.
Absolutely. Thank you.
Sure.
Is there any follow-up mission that's going based, and the other question would be is, knowing what you know now, is there an instrument you wish you had on the spacecraft that's not there?
Okay, let me answer those in reverse order. So even before we got there, we knew that we really wished we had a dosimeter. So we have things to measure the radiation that hits the spacecraft in various ways, but we don't have something that's designed to just measure what's the total radiation dose we're getting at various energies. The high energy stuff that would damage electronics. Early on, we wanted to put one of those on. We didn't ask for it before we, in the proposal. After we wrote the proposal and got it approved, we thought of that, and we went back to NASA and said, you know what, it would be really smart to have a dosimeter. The next mission to Jupiter is going to be really happy if we've measured the radiation better. Measuring the radiation will help us predict how, when it's going to fail and so forth. And they basically said, we don't want to spend that money. So that's the thing I miss the most, is a dosimeter. In terms of the rest of it, the mission and the follow-on mission, we like to say that we're our own follow-on mission. If you look at the questions that came up in our first 5 years, our prime mission, a lot of them we can try to address with the extended mission, because as that perijove moves north, we get to look at all the different territory. As we try to understand what's going on with all this complexity to the atmosphere, more data, a finer structured map helps with that. So measure the magnetic field more finely, measure the gravity more finely, and look at things like the effect of the tides from the moons on Jupiter. Measure it over a greater period of time, look for things that change with time. So the kinds of follow-ups that we want to do mostly are things that we can actually make some attempt at in the extended mission. Now, sure, I'd like to have, another few channels for the microwave radiometer or things like that, but we knew that before we got there. You're limited by, time and money and mass. In terms of, did we send it with the right instruments? Pretty much, I think, yes. The answer is yes. And that's another way to say that is everything we measured gave us a surprise. So that tells us we're measuring the right things.
Thank you.
I do have one more thing I want to show you guys, which I hope you've already seen, but just in case, I'm going to share my screen again. Okay, and if you go to your favorite search engine, you put in Mission Juno, up pops the Juno website. And remember I talked about, but I haven't shown you anything from JunoCam? the visible light camera that we threw on there mostly for outreach. Well, we're doing tons of science with it, but we take it seriously that it's an outreach camera. So what we do with Juno Cam is we take the raw images collected by the camera and we dump them out on a website and let anybody who wants to play with them and turn them into things like what you're seeing over here. So if I go here, and if I look just at images generated by our folks, we get things like this. Little slivers where this is what the raw data look like when you take a camera that takes 3 color pictures. It actually has 4. It has the usual 3 colors to make a color image, and it has a methane filter to look at clouds in a particular way, in the methane clouds. But those are separate images and they're little slices because that's the way the camera works. It's the way most cameras in space work actually is you have to put the data together to make an image, right? So we take all those images and we just deposit them out on the web. Get this to go away. While I'm sharing my screen, I can't figure out how to get it to stop showing me that picture. Here, let me do it this way. Go back. Okay, now, if I look at pictures made by the public, and I'm gonna cheat and go right to the ones, featured ones, which are ones that actually Candy Hansen is the scientist, has looked at and said, those are really cool. Why am I getting no results? Let's do it this way. Okay, y'all seeing that now? So one of the other ways in which we were surprised by Juno was we had this great idea of let's just let the public, anybody who wants to, process our data from the camera. And the surprise was just how amazing a job people do with that. So every one of these images is done by citizen scientists or artists, people who took the Juno Cam data and processed it to produce these spectacular images. They've adjusted the color scales or the contrast. They've put together those pieces to make a composite. They've put together collages to get a bigger piece of the planet shown. They've done made movies out of consecutive things. They've done science with it here. These are people. Who is this guy? This was Bjorn Johnson, has taken these images and marked various parts of the planet so that people can do science with it. There are people, I don't recognize this one. Oh, I think that might be Ganymede. Anyway, I won't go through all of these because there's a zillion of them and you can do it yourself. It's all there just by looking for Mission Juno. But what we found is, you know, the line from the movie is, if you build it, they will come. You don't even have to build it. If you give people the bricks, they will build it. They will come and build it. So we've had amazing experience with that. It's open to anybody. If you're good at image processing or you want to learn, go to Mission Juno and find the raw images and start playing. If you like to mess around with images and see what you can see with them, start with somebody else's image that is made and posted on the website, and put it in Photoshop or some other program and start playing with the color scales and see what you can bring out. There's some stuff on there about how to give credit to people properly and all of that. But if you like messing around with images of planets, I highly encourage you to go to the Mission Juno website and see what's there and see if you can contribute. It's been a lot of fun just seeing who's out there. And people have done amazing artworks. They've done serious science. There's been multiple science papers now published using JunoCam images, using the data, from people who were not associated with our team, except that they volunteered to play with the data. Probably half the really good ones have involvement from a guy named Gerald Eichstadt, who's in Germany, and his day job is some kind of mathematical fluid dynamics thing, unrelated to astronomy. But he got interested, figured out how to make the pictures, and he does it so well that lots of other people use his as a base. And he's been studying the fluid dynamics of Jupiter. Oh, and we also sometimes have a use for amateur photos of Jupiter because they give us context. Remember, we only go by every few months. I think we're at 43-day orbits now, and we'll be 38-day orbits come October. So for the 43 days in between flying by Jupiter, it's nice to have images to provide context so that when we get the data, we know what was going on before and after we were there.
We've made a few images like that at Mount Wilson with the 100-inch telescope.
Right.
I think Glenn Norton might have been involved with that. But
Yes.
but I have a question which almost nobody ever asks, but probably should, and I'm sure everybody will be curious to know the answer. But what does a chief scientist do?
So, chief project scientist, that's me?
Yeah, but that's what.
Yes.
Yeah,
Um,
you.
Okay, so it's a little complicated, but the simplest way to describe it is most of what I do is I translate science to engineering and engineering to science. So it depends on which phase of the mission. Another way of describing it is the principal investigator's in charge of everything, but he's in Texas, and all the day-to-day stuff is happening, or a lot of the day-to-day stuff is happening at JPL in Pasadena. So he needs somebody in Pasadena to represent the interests of science. That's me. But a lot of what that means is the engineers who built it when we were building it, or who were designing it, designing the spacecraft, and the engineers who operate the spacecraft now, basically, to do the job right, they need to know what they need to do to give us the best science. The scientists, to do the job right, need to know what the engineering constraints are, what the limits are of what they can do, and somebody has to explain one to the other. That's most of what I wind up doing, because I'm the guy in between telling the science team, I don't think they're going to be able to do that, but what if you try to do this? And then telling the engineering team, I know you really think it's not safe to do that part, but can you get us closer to this, because that'll get us the measurement we want. Or if you want to do this kind of measurement, you better tell us 3 months in advance, because it's going to take a lot of effort to make sure that's safe. And if you want to do that kind of measurement, we can do that tomorrow. Just send up a command that's already stuff that's been done. That kind of interface of being somebody who understands the science and understands the engineering, that's mostly the job of a project scientist, at least on Juno. I also get to run science team meetings and do outreach and stuff like that. And the coolest part is anything going on the mission, I can stick my nose in and try to understand and see if I can contribute to. So every time there's an important decision, I have a seat at the table, and provided that I'm not talking nonsense, if I'm actually saying something useful, I can contribute and try to solve or help solve anything that comes up. So for a guy like me, that's the best part. That's a whole lot of fun, problem solving and figuring out, hearing about things I never knew anything about, and trying to still be part of the team and contribute to it. So long as I'm being useful, everybody's willing to have me participate.
How often do you communicate with the satellite? You use the Deep Space Network?
We use the Deep Space Network. Juno's pretty far away. Jupiter is far enough that it takes light somewhere between half an hour and an hour to get there, one-way light time. So, and we're solar powered, and we're 5 times further away from the sun. So we're running the whole spacecraft on about 500 watts. So we can't afford to communicate too often. It's every few days, something like that. And also remember, it's a spinner. So our antenna is aligned with the spin axis. And we basically have to point the spin axis at the Earth to communicate. Jupiter's orbiting, spacecraft is orbiting Jupiter. So every few days, if you want to communicate every few days, we have to fire the thrusters a little bit every few days to align it with the Earth again. That takes fuel. We don't have any more fuel coming. So we don't want to try to keep it in contact all the time. And then of course, when we do a perijove pass, if we want to measure the gravity, we don't want to fire thrusters anywhere near the perijove pass, because our gravitational measurement relies on the only thing making the spacecraft do what it does is gravity. So you fire a thruster, you screw that up. So typically we align it to communicate with the Earth right before perijove, like a day before, and then leave it in that attitude, and that lasts long enough to communicate through perijove and get the gravity data. And then a day or so after perijove, we have to turn it again to get more data down. And we, like most missions, I think we use a lot more data than we originally thought we were going to. So we're using 70 meters every few days. And I think in the original proposal, we were probably talking 34-meter antennas, once a week. We running out of steam?
Looks like it. Take over, Ron.
Running out of ion propulsion.
Well, I guess I can think of one more question I was curious about. Did you learn anything new about the Great Red Spot?
Sure. We learned it goes deeper than most people thought it would. We don't yet have a good handle on why it's shrinking. Everybody can see it's shrinking, but we don't know exactly what's happening there, although it's probably not losing as much. It's probably not going away anytime soon. The gravity signature, trying to remember the depth. Don't quote me because I probably have the number wrong, but you can look it up. The gravity signature shows that it's something on the order of, or shallower than, I think it was 600 or 800 kilometers deep. And the microwave radiometer signature shows it goes at least a few hundred kilometers. So that's a pretty good handle on the depth. And that tells us something about how it formed. Cheng Li, one of the guys on our microwave radiometer team, is working on a paper that'll give a pretty good model of the Great Red Spot. But I don't want to spill the beans because he hasn't published his paper yet.
So can you tell if it's shrinking as a function of depth? Is the shrinking just at the surface, or is it getting like less volume or something?
I'm hesitating because I think the short answer is you can't really tell that yet, but I wouldn't want to swear to it because Cheng's still working on it.
Uh-huh.
What we see, we don't have the same resolution with the microwave radiometer. It's a big fat antenna beam. It's 20 degrees across. So when we see the Great Red Spot with the microwave radiometer, particularly at the deepest part with the lowest frequency channel, we're resolving it, but we're not resolving it with much detail. So you're not going to be able to look at it and say, oh, it's smaller today than it was, you know, a year ago or something. And plus, of course, we don't fly over it very often. We don't have a lot of, we only really have one really good pass over it. But if you understand what the size is as a function of depth and what the temperature is as a function of depth, that helps you model it, and you might be able to have a model that tells you, you know, that explains what we see at the surface, and would then make a prediction about what it should look like at depth.
Thank you.
Thank you. It's been fun.
Well, I guess that's our meeting for tonight, right?
Well, no, you're in
Thank you.
charge. What do you say?
Yes.
I was asking Gary, since our president isn't here.
Oh,
he's-
Gary's in charge. Who's in charge around here?
There- Nobody's in charge. It's obvious. So I'm just amazed, you know, that, you know, I would think that if you found something, the first thing you have to do is say, well, we need to send a command to the spacecraft. And now we have to get permission from the Deep Space Network because, you know, they're busy, you know, so there's a lot of people that are involved in something like that.
That's absolutely true. And we generally, the way it works is the time periods when we're going to communicate with the spacecraft are scheduled months in advance. So we know which antenna we're going to use at which time, and negotiate that with the Deep Space Network and all the other people who want to use those antennas. And then which commands we send up are usually determined in a process that starts maybe a couple months before the command is actually sent up, and finalized mostly a few weeks before they're sent up, but potentially as late as, you know, a day, depending on what's going on. But it's not like, say, a Mars mission where you drive the rover and you know, every day you figure out what commands you're sending up tomorrow. This is, you know, it's days in between command passes. Perijove time is very precious. You want everything. You don't want to make any split-second decisions during that 2-hour Perijove pass. You want everything to be predetermined and just run like clockwork as it goes through. And you're going through every 43 days, you're going through this high-intensity radiation environment that's going to mess things up potentially. So you don't want to do anything risky. Speaking of not doing anything risky, I'm gonna say goodnight and get back to my wife, who's been waiting patiently for a while.